Right, we have been discussing transformations, right? Coordinate transformations. Now, if you recall, do you recall what was given in the exam? The problem which was given in exam? The problem which was given midterm, yeah. So what was it? No. With regards to coordinate transformation. Huh? Right. So, huh? Yeah, do you remember, I don't want you to remember the numbers exactly, but do you remember what was given to you? Kind of, maybe? Yeah, so what was happening there? Did you realize what was happening there? Or? There was no vector over there. That's not a vector, it's an angle. There was no orbital, there were orbital elements, but there was no vectors. What were those? See, what you learned, this is what you learned. Coordinate transformation. You have, and when you're asked to identify a coordinate frame or a reference frame, you need to give me 3 basis vectors or 3 axes. Understand? Some of you, for example, you were asked equatorial coordinate system. Some of you have pointed me to the plane. Some of you have pointed one axis or axis. You have to give me at least 2 axes to identify a coordinate frame. Get it? For defining a coordinate frame, you can either use 2 directions or a plane and a direction in a plane. Right. You could have just drawn it, or they were actually, the ECI frame was right there, right? ECI frame was, every axis was right there. Even the perifocal frame was right there. The perifocal frame was what? You remember? No? The perifocal frame, PQW frame. How did we define PQW? No? How did we define PQW? We defined PQW directions. Huh? No. Again, see, this has been done several times. At least, I have told you at least 10, 12 times, okay? How do you define a perifocal frame? So you have the P direction. What is the P direction? P direction? You shouldn't say it that way. You should say periapsis direction. It's in the periapsis direction, right? P direction. Correct? This is P. This was given in the in that figure. This direction was there. What was the other thing we defined? There is no PQR, it is PQW, it is not PQR. What is the W direction? How did we say W was? W direction is this. It's the angular momentum direction. Right? So W direction is always this. And W direction was also there. If you look at the diagram, the W direction was H direction. Right? If you have P and W defined, so this is your W. Your Q would be cross P. Should complete the right-handed system. Okay, so this would be your Q. So you see P, Q, and W. These are specific directions, right? This P, what is this P? Periapsis. What is periapsis? You're getting there, yes. Right, you're right. So it is called the closest point of approach. The orbiting body's closest point of approach to the central body. You're right. Focus or central body. Okay. So this is the closest point of approach, and the line joining the focus and the periapsis is the periapsis direction. Right. That is your P direction for the perifocal frame. Perifocal frame is PQW. And which was the other frame over there? ECI frame. So it is the equatorial, geocentric equatorial frame. So if you look at the geocentric equatorial frame, what are the two directions you can define? You cannot just say I and J. It doesn't matter what letters you use. You have to define that direction. It has to point somewhere. So how do you define that direction? You define the X direction. The X direction is defined, right? How is the X direction defined? This points to the constellation Aries. Okay. This is always defined, or vernal equinox. Okay. Which is the other direction? Equator is not a direction. You're right. Equator is correct, but what is it? The other direction is this direction. It is north direction, yes. But how do you say this? It's not north direction. It is the axis of rotation. It is the direction of axis of rotation. See this. So your Earth rotates in this direction, right? So the axis of rotation is this. This is defined. Z is defined as the axis of direction. This is generally the north. Okay. Now, how do you define Y? Right. Y is just the completes the right-handed rule. X, Y, and Z. Or if you have Y, you have Y, Z, and X. Okay. This is cyclic. So if you change it, for example, if you change it Z, X, Y. Okay, these are always cyclic. X, Y, Z. When you say cyclic, what do you mean? This moves here, this moves here, and this moves here. You see the cycle? Cyclically, they're all equal. You can write them like that. You cannot write Y equal to X cross Z. That is just another system. Cyclically, you can interchange. So these are the three directions. When you're asked to give the a coordinate system or a coordinate frame, you should be able to give me at least two directions or one plane and a direction in that plane. If you had told me the ecliptic plane and the perigee direction, so if you're giving me the plane, ecliptic plane, what are you giving me? You're actually giving me the perpendicular to that plane. Okay? Perpendicular. You actually define a plane using the perpendicular. Can any plane have two perpendiculars? It has to have one, right? It has to have one normal to it, right? A normal to a plane is always just only one. If you look at the direction, so again, this is the direction, right? The normal direction. So the ecliptic plane is, what is the ecliptic plane here? Here, what is the ecliptic plane here? The board is the ecliptic plane. Okay, and what is the direction of the orbiting body? Is it clockwise or anti-clockwise? Huh? Counterclockwise. It's fairly simple. See, look at this. This, right? It is counterclockwise. This direction. Get it? Or always counterclockwise. So this is always counterclockwise. Okay? So when you're talking about coordinate transformation, now is the ECI frame and the perifocal frame clear to you guys? Everyone? If I ask you the same question, you're not going to go haywire. You're going to give me the correct answer. All right. Now, if you look at the ECI or geocentric equatorial frame, if this is transformed to perifocal frame or the PQW frame, yes, what is the question? So how do you go from equatorial frame to perifocal frame? You had a question? Who had a question? Ms. Davis, you had a question? To whom? Okay. So how do you go from geocentric ECI or geocentric equatorial frame to perifocal frame? How did we say we go there? Right. We do a 3-1-3 rotation or Euler sequence. It's called Euler. You have to understand a little bit of history behind this. Okay. It is Sammy. You want to come here and explain? No. You want to come here and explain? Okay. And you want to let me explain? Okay. If you're looking at the Euler sequence, see, Euler immediately noticed that if you do a 3-1-3 rotation, right, from an equatorial frame, reference frame, you would land in a perifocal frame. Okay. Huh? Yes. So this particular sequence was his invention or was his discovery. It is not invention, but it is discovery. He discovered this. Okay. And he essentially named these angles omega, I, and small omega. All right. Traditionally, or if you look back the history of celestial mechanics, this is the originator. This is called the Euler sequence. But you can take into account any sequence. Essentially then he came up with the theorem that you could go from one rotation to another or from one frame to another using any 3 rotations. Okay? So you could do 2-1-2, 1-2-1, or 1-2-3, 3-2-1, 1-3-2. If you look at the rotation sequences, there are essentially 2 types of rotation sequences. Okay? One is symmetric rotation sequences. You see the symmetry here? And the other is non-symmetric rotation sequences. Okay? You can call all of this as Euler sequences. All of these are called as Euler sequences. Alright? But this particular Euler sequence, see, as aircraft engineers, as aeronautical engineers, this is not of high significance. What is your sequence when you're talking about aircraft? What sequence do you follow? Do you know? You generally go by yaw pitch roll, right? It's a 1-2-3 rotation sequence. That is of high importance. That is how you communicate as an aeronautical engineer or an aircraft engineer. You're always talking about yaw pitch roll. When you're talking about space, you're talking about these 3 angles. You don't talk about yaw pitch roll. You could talk about yaw pitch roll, but it doesn't make a lot of sense. Okay, so this sequence is of very high importance to spacecraft engineers. So 3-1-3 Euler sequence. Now what happens here is, you looked at this, right? If you have this sequence, now if I want to develop the rotation matrix or associated with this sequence, what I do is I multiply right? You understand this, correct? Everyone is familiar with this. This is the rotation matrix or direction cosine matrix, which transforms a geocentric equatorial frame to perifocal frame. This is a 3 by 3 matrix. All these three are 3 by 3 matrices. In examination, in midterm exam, what you were given was, you had this, right, as just pure numbers. You were asked to compute this. So you can go from, these are called Euler angles, okay, cap omega I and small omega. You can go from Euler angles to DCM by using this rotation, or given a DCM, you can calculate the Euler angles. And these Euler angles will change if the sequence is different. It's different from 1, 2, 3 to 3, 1, 3. Okay. So if you do a 1, 2, 3 rotation by, you will not end up with the, if you do a 1, 2, 3 rotation from this to this, you can still do 1, 2, 3 rotation from going from this to this, but the angles will be different. It will not be these angles. It will be some, the general angles used are 1, 2, 3, psi, I think, phi, theta, psi. This is also mostly your yaw pitch rule, if you remember. Pi, theta, psi, right? These are the angles you use for yaw pitch rule. These are the general angles. You can say these are the general angles. These have got nothing to do with orbital elements. Okay. Now, if you look at these are actually part of orbital elements as well, right? These define the orientation of the orbit. So this is the significance of Euler angles and Euler sequence. If you're given in exam, what you were given was this matrix. And if you look at this matrix, let me pull up this matrix, okay? All right, look at the DCM here, okay? If you're given this DCM, this is the rotation matrix or the DCM associated with 313 sequence. Which angle would you first calculate? If you're given this DCM and you're asked to compute the three angles, which angle would you first compute? Try to make some sense. Try to be logical. Huh? Look at it and tell me which angle would you first calculate. Why I? Exactly. So this is given. If you look at this, all these are just numbers, right? If you just multiply, it will all be just one number. You cannot calculate cap omega from this value or small omega from this value, right? Because there are two unknowns and one known. So the first thing you are going to do is you are going to use this cell to calculate I. Once you know I, you can use this to calculate one of the other values. Okay? Now, why did we use if you recall, we used a fraction, or we said we used these two, not these two. We used these two to calculate cap omega. We used these two to calculate small omega. Why did we do that? We could have just used this one, right? Once we know I, we can just use this one. Or we could just use this one to calculate small omega. Why did we use two? No, I know I have calculated I here, right? I have calculated I, right? I can use, if I just substitute for that I, right? I can get omega, right? Why did I use these two? Huh? It's not about steps. It is not so much about steps. See, what does I do? You have to understand what does I do. Cosine of I is also equal to cosine of minus I, right? So when you do calculate I, is it I or minus I? I would suggest you go back and read. So this I and minus I will define whether it's a prograde or a retrograde orbit. So this is a very basic way of, if you just have these elements given to you, you will have no other way but to, if you're just given this DCM, so if it is positive I, it's a prograde orbit. If it's a negative I, it's a retrograde orbit. You know what prograde and retrograde orbits are? Yes. What is prograde and retrograde? Direction of rotation of the central body. Retrograde would be opposite. Okay. So this one information which will always be given to you is whether it's a prograde or a retrograde orbit to calculate this I. Now, similarly, when you're calculating omega, you want to make sure the omega value is not either or. Okay? So when you do this, if you do a tangent, right? You have tangents. So tangent is, everything is positive here, right? This only sign is positive. Here cosine is positive. You remember this. It is all silver teacups. All silver teacups. So you have, if you have sine omega over cosine omega, if both these are positive, where does the value, the quadrant lie? The first quadrant, right? If this is negative and this is positive, second quadrant. If this is negative, this is positive, and if both are negative, it lies in this. Now what happens here is, you should understand, if you're looking at these two separately, you can figure out which quadrant. But if you just divide, the whole number is either positive or negative, right? See, for example, if these two are negative, the whole number is positive, right? At that point, see, you'll always just end up with these two values. You will never realize whether if it is in this or this quadrant. If you look at the whole number, okay, and this helps you when you divide this by just looking at these signs. It will help you which quadrant, and accordingly what is the angle, what is the actual angle. Okay, that is the reason you take the ratio. So if you calculate tangent inverse, what is tangent of something? Tangent omega is sine omega over cosine omega, right? Now if you want to calculate omega, you're going to do tangent inverse of that value, right? Sine omega will have a value, cosine omega will have a value, right? Now tangent omega will be just one number, right? Looking at that number, you cannot figure out, just looking at that number, you cannot figure out, if I just take the ratio of these two numbers, you cannot figure out which quadrant that angle will lie in. No? Still not making sense? So tangent of, let's say, it applies to the problem. That's the reason you were given the. Your calculators are, if you just input a number, if you just input the ratio rather than inputting to the two numbers, your calculator will always throw a value either in this or this. If you do separate numbers, it will always give you either it's this or this. Huh? So tangent of, let's say, minus 45. Where would this lie? Huh? What is tangent of minus 45? None, 0. It's 1, right? Yeah, degrees. So tangent of minus 45 is what? 1, right? Okay. So tangent of minus 45 is 1, but this could be sine of minus 45 over cosine of 45, minus 45. Sorry, 45. Hang on. So let's do this. All right. So tangent of of 45 is negative 1. 1. Okay. So this could be sine 45 over cosine 45, right? So let's say some angle. All right, let's do this. Tangent inverse of 1 is equal to what? Tangent inverse could be 45 degrees or 180 plus 45, 235. You see it? Similarly, tangent inverse of, let's say, 0, not 0, minus 1 could be so you really need to look at the ratio to figure out which one is negative. So when you're figuring out cap omega and small omega, cap omega is the this is cap omega, right? X to ascending node. It could be this value, or it could be 180 plus the other value. So you don't know which one. But if you look at this ratio, you will always know whether sine is negative or cosine is negative, or which one is, if both are negative, you'll know. So now you'll be able to figure out exactly what angle. Okay? Because see, if it changes, what happens is, if this omega is different, you may think your orbiting body is here, but it may actually be here. Okay? So what we looked at in the exam was, just give me a couple more minutes. You were given this, and you were asked to calculate these three angles. So the way we go about calculating is, we look at which is the first value we can calculate. It's this one. And then we use the ratio of these two and these two to calculate cap omega and small omega.